Right, so this week we're very happy to have Hugo Touchette from South Africa, Stellenbosch, South Africa, from the Applied Mathematics Department, and he'll be telling us more about the large deviation approach to statistical physics. Please go ahead.
Thank you, Janusz. Thank you for the invitation. Pleasure to talk to the Dutch Institute for Emergent Phenomena. I hope to be able to visit at some point. So the goal of the talk is to give an introduction to large deviation theory and then show how it's being applied in statistical physics to study many particle system. So I'll go through some historical presentation of the subject, and then I'll cover the applications for equilibrium and non-equilibrium systems. So I'll start with a bit of history in large deviation theory, then present the basics, but the really basics of large deviations, the basic result that we use in statistical physics, and then I'll present two applications, one for equilibrium and another for non-equilibrium, and I'll finish with a panorama of more applications that are being studied in physics. So not just for equilibrium and non-equilibrium, but also for complex systems. Now, these are the themes. So what we'll study are systems with many components. So in the case of physics, many particles, but it could be some other things like graphs, so many components, correlated processes that have many states or high dimensional states. So I'll cover some of those. And then what we'll study are typical states and fluctuations around typicality. And then what we'll see is that probabilities have an exponential form, and this is the basis for concentration of probability. So we'll see typical states appearing and very low probability for fluctuations around those typical states. And here I thought I could plug the word emergence. This concentration of probability is really the basis of what we call emergent determinism. So you start with a stochastic process, but what you see at the macroscopic level is something that's entirely deterministic. And this has to do with large deviation theory and this concept of concentration of probability. So we'll get to this. What I'll start with is the history, which is very interesting. If you talk to physicists, actually, large deviation theory, they will say we'll start from Boltzmann, but it's got a totally independent history on the side of mathematics. So on the math side, it starts with work in Kramer in 1938, and then we'll see this. So it has really like two independent streams or two independent routes in physics and mathematics. And then the merging of the two routes or the two developments actually came only much later, around the 1970s and the 1980s. And now we're fortunate to be at a point in time where actually physicists and mathematicians are aware of that common history and the common results. And then we're using a lot of results coming from maths to study physical systems, but also what's been interesting is that from physical applications, we've been able to develop the mathematical theory as well. And I think I'll be able to give you some ideas of this. Okay, so as I showed there, it all starts from Boltzmann, but it depends who you talk to. So if you talk to physicists, they know this calculation, and it's only been realized rather recently, actually, that calculation has to do with large deviations. And so mathematicians now are not fully aware of this, but if you present that calculation to them, I think they will realize that this is large deviation theory. So this is from the paper of Boltzmann from 1877, which is the paper that introduced the entropy, the statistical notion of entropy. So this is a very important paper in statistical physics. And the problem that Boltzmann was considering is you have a collection of n particles. So you have 1, 2, 3. So this is the particle number. And then Boltzmann assumes that you have each particle can take one of many energy levels. So you have discrete energy levels for each particle, and then the particle can be in one such energy level. Now, this is quite amazing. If you think that this is before quantum mechanics, why would you consider discrete energy levels? And then for Boltzmann, it was just to do combinatorics, to do counting, and to just simplify the problem. The real problem that he wanted to look at was the perfect gas and then trying to derive the entropy for the perfect gas. But let's start with the discrete problem. So you have the particle, and so if you specify the energy level for each particle, what you're specifying is the microscopic configuration. That's the microstate. But what you're interested in is not really the microstate. You want to look at some macrostate. So that's the macroscopic description of the system. And here the macroscopic description is the energy distribution. So here you want to report the number of particles in each energy level. So you look now at the y-axis, and then you just count for each energy level how many particles are there. For a given microscopic configuration, this is just the empirical distribution of the energies. So that's the energy distribution. If you have a different microscopic distribution, a microscopic configuration, you're going to get a different energy level. So that energy distribution is a kind of random variable. Now, Boltzmann knew, and then we know in statistical physics, that if you want to do thermodynamics, what you need to calculate is the number of microscopic configurations that give you that macro state. So you want to calculate the number of macro states that are consistent with some energy distribution. It's clear that if you fix the energy distribution, there might be many microscopic configurations that have that same energy distribution, so you need to count it. Now, the counting comes from the multinomial distribution. It's the multinomial factor. So if you fix the W's here for the energy distribution, then this is just a multinomial factor for counting the number of microstates. So that involves the factorial. If you take the log of this and then you approximate the factorials using Stirling approximation, what you get on the log scale is the entropy. So this is the entropy that you see in information theory, but this is the entropy that appeared really in Boltzmann paper in 1877. So that's the P log P. This is the excerpt of the Boltzmann paper where you see this entropy. So the entropy is M. So you see that W, L, W. For Boltzmann, L is the log. So this is really the P log P entropy. The second equation here is the particle conservation. So if you sum up all the occupation, you get the particle number. And this one here is the energy. So if you sum up the energy with the number of particles in energy level 1 and then so on, then you get the total energy. So Boltzmann here actually maximized the entropy with those two constraints. So you see the maximum entropy principle appearing already from 1877. So that's quite amazing. This is an amazing paper. Not so easy to read. You need multiple passes of reading to understand all the details, but this is a very amazing paper. The upshot for us is that if you assume that all the microscopic configurations have the same probability, then you come up with a probability for the energy distribution that says that the probability for the distribution, so the energy distribution, goes down exponentially with the number of particles, and the exponent is the entropy. And the reason why we have an approximation sign rather than an equality is because we're using Stirling approximation to approximate the factorial factors there. So that's the first instance where you have this exponentially decaying probability, and then we'll see that that's the common theme for large deviation theory. Now, there's a lot of hindsight actually when I explain this, because I talk about probabilities, but it's not so clear in Boltzmann's paper, so we'll come to this. Now, this is a calculation actually for independent particles. You only look at the energy of each particle, and then there's no energy for the correlation or for the interactions between particles. So it's a rather limited calculation, and here you can do the combinatorial, you can do the counting because it's a simple model. Later on, Einstein came in 1910 and then looked at the problem of generalizing that counting calculations from Boltzmann. So the goal here is to try to do more or less the same thing, but you want to look at a physically realistic system with interactions, maybe even something that's fully realistic, like a normal gas with collisions and interactions. Now, as you can imagine, then in that case, you cannot do the counting. So what Einstein actually did is to reverse the reasoning. He would say, we cannot do the counting from microscopic principle or from a microscopic level. What we'll do instead is that number of microstates that have a given macro state will just say that this is actually given by the entropy. So this is Einstein postulates. So here it's a general framework. You have a physical system with n particle, and then you look at some macro state Mn, which could be anything. It could be the energy distribution, it could be the magnetization, it could be the kinetic energy of the system, and then you want to count the number of microscopic configurations that give you a value of that macro state. Now, because you cannot do the counting, what Einstein postulates is to say that that number will be the exponential of some entropy. It doesn't mean that you gain much from this, but actually you do. You can derive pretty much all of thermodynamics just out of that postulate. In particular, you get probability distribution from the macro state, and then the equilibrium state for the macro state, so the most probable macro state, will be the one maximizing the entropy. So you recover already something that was known from Boltzmann. And moreover, if you look at expansion around the equilibrium, then you get also heat capacity factors related to the second derivative. So there's a lot actually in that postulate, but here you're trying to generalize this idea that probabilities are exponential and the exponent is the entropy. So that's the excerpt from Einstein's paper. At that point, there's no suggestion that this goes beyond physics. These two papers are really about physical systems, so there's not even a suggestion that these exponential probabilities could give rise to a structure for mathematics or dealing with random variables. At that point, anyway, probability theory was pretty much in its infancy, so there was no connection onto maths from physics. But nonetheless, what you see is that probabilities have an exponential form. So that's basically the start on the physics side. If you go on the mathematical side, you have to wait until 1938 to see these probabilities that have exponential factors appearing. And the first result, and this is where if you talk to a mathematician, then they would say the first large deviation result is from Kramer in 1938. This is a French paper that was part of a proceedings in Switzerland, in which Kramer actually considered the fluctuations of a sample mean. And the reason why Kramer was interested in this was because of applications with insurance. It was actually all his life he was interested in actual mathematics. And then at that time, they were using central limit theorem to find Gaussian distributions of random claims that a company would receive. But this is not very good because you don't get a good approximation of what the tail of the distribution is for a claim for an insurance company. So Kramer wanted to go beyond the central limit theorem by looking at the fluctuation of the sample mean. So you take a sum of random variables, you take them to be independent, identically distributed, and then you take the 1 over n, and so you have the sample mean. So what Kramer showed is that you can get the distribution of that, and you can get it from the cumulant function. So this is the cumulant function of the random variable, and he showed that the probability distribution of the sample mean will have an exponential term with the number of random variable, and you have all sorts of corrections that are beyond that exponential term, corrections that you can actually get by kind of a perturbation series from the cumulant. But what's important is the dominant term of that approximation, which is the decaying exponential. You see all the other corrections are kind of 1 over square root of n, 1 over n. So they're tiny compared to the fact that you have that decaying exponential in front as the dominant term. And the exponent, which we call now the rate function, Kramer actually showed that it's the Legendre transform of the cumulant. So you have that relationship between cumulant and the rate function for probability. So this is very interesting, and then we'll see how it generalizes later. So this is a very important paper, but it's somewhat got unnoticed actually for a very long time. People, again, were studying mostly the central limit theorem, so it took a long time before people started realizing that going beyond the central limit theorem is something useful and important. So when I had to wait for the next large deviation result to come until 1957, a paper by Sanof, a Russian mathematician, who looked at a problem that's very close to Boltzmann. So he looked at a sequence of independent random variables. They have the same distribution. And now you want to look at the empirical distributions of these random variables. So to fix the ideas, for instance, imagine that the random variables are binary random variables. So it's just a bunch of zeros and ones. So if you throw a given sequence, you can calculate the number of zeros in the sequence, divide this by n, and so you have the fractions of zeros, and then you can do the same thing with the ones. This is the empirical distribution of the sequence. If you throw another sequence, you get another empirical distribution. So this is a random vector. You have two components in the vector. This is an empirical distribution. It's a random variable. It's a random vector. So what Sanof calculated is the probability that you see a given value of this empirical distribution. So a given fractions of zeros and ones, if you look again at the particular case of binary sequences. And this probability is nothing but the multinomial distribution. And so again, you can use Stirling approximation, and then you get that the probability decays exponentially to dominant order in n, and the exponent is from the Stirling approximation, what you get is the relative entropy. So this is positive, and it has 1, 0, and the 0 will correspond to the point of the probability where you don't have the exponential decay, and so you recover the concentration of the probability towards that 0, and the 0 here is the empirical distribution being equal to p, which makes sense. If you throw a random sequence of zeros and ones with probability 1/2, 1/2, the most probable sequence are those that have a fractions of zeros to be close to 1/2 and a fraction of ones close to 1/2. But what you get out of this result is actually it's very quantitative. the probability that you depart from 1/2 in terms of observation is exponentially unlikely, and it goes with the relative entropy. This is the excerpt where you see this result. This is a Russian paper. It's been translated in English actually by the American Army, so you can find the PDF of this. It's a very interesting paper because there's no mention of Boltzmann. Although when you read this, I mean, if you've read Boltzmann papers and you read this one, it's really much the same. It's the same problem. It's just written in a more mathematical way, and it's 80 years after. But there's no mention of Boltzmann or any connection there. And what's more surprising is that in Boltzmann's paper, he wanted to look at the perfect gas, so continuous random variables, but he started with a discrete problem. And so near the end of the paper, he says, well, to treat the continuous space problem, what you do is that you discretize and then you take a continuum limit at the end, which is natural for physicists and even for mathematicians. What's interesting is that when you read Sanof's paper, he does exactly the same. He starts with a discrete problem, but then he says, oh, we can also treat continuous random variables with this. What we do is that we discretize these random variables and then we take a continuum limit, and it's exactly the same. It's just, again, written in a much more mathematical way. I've tried to find connections, more historical connections. What's also surprising with this paper is that it's the only paper of Sanof that relates to probability theory. He was working more on the side of number theory, and he was also involved in the teaching of mathematics in North Korea in the 50s. So there were lots of exchanges between communist Russia and communist North Korea, and then they sent Sanof to oversee the development of a mathematical school there. So there's not a lot of information beyond this. I've looked with my Russian contacts but couldn't find more. If you know anything about this, I'll be more than interested. It's clear that Kolmogorov was actually, so he did that paper when he was in Moscow. Kolmogorov was around that time, so there must have been some conversation. So it's a bit surprising that there's no mention of Boltzmann. I'm pretty sure that Kolmogorov would have known about Boltzmann, but this is conjecture anyway. Okay, so that's the second large deviation result, where you see probabilities appearing with an exponential, but these have to do now with independent random variables. So it took a long time before people realized that there was a lot more to the story. And so I'll stop the history there, and I'll just present now how we understand large deviation theory in a general way. So it's not something that you apply only for independent random variables. Obviously, I'll come to applications later for correlated random variables. So now large deviation theory, the way it's phrased is in a very general way that you start with a random variable, which is a collection of random variables, a family of random variables. So you have a random variable parameterized by some parameter n, and then n at some point will go to infinity. So n is just a parameter, so you have a family. What you're interested to study is the probability distribution of that random variable. So it could be a density or a discrete distribution depending on the nature of the random variable. What you're expecting is that that distribution will go exponentially. And so in the theory, this is elevated as a definition, and it's called the large deviation approximation. So you'll say that the probability or the random variable itself will satisfy a large deviation principle if the distribution goes exponentially down with n, and then you have some exponent there which describes the speed at which it goes down exponentially. Now, this is the way I would write it myself with the approximation sign. This is what physicists would do, but of course for mathematics this is insufficient. So what's the meaning of the approximation? Again, it relates to what I said before. This is the dominant part of the distribution. So if you take the log of the probability, then you have something that's proportional to n, and then you have other terms, but they'll be smaller than n. So there'll be small o of n. So it means that if you divide by n and then you take the limit, then you're going to kill all the corrections, and then you'll retain only that exponent, which we call the rate function. And that rate function is always positive. We know this. Now, so we'll say that the random variable or the distribution satisfies the large deviation principle or the large deviation approximation if this limit exists and gives you a function which is nowhere 0 or nowhere infinity. Not everywhere 0 and not everywhere infinity. Now, mathematically, it's even more complicated. As you can imagine, you have a limit sup, a limit inf, so the two limits need not be equal, but in most cases, for most applications, actually, the two bounds will be the same, and so you have the existence of the limit. And this is what we consider mostly in physics. So at this point, really, the theory is all about this definition, this large deviation principle. For a given sequence of random variable, for a given random variable, you want to show that that random variable satisfies the large deviation principle, and then you want to obtain the rate function. The rate function will give you basically a snapshot or an understanding of what the distribution looks like on the exponential scale. And this is what I'm showing here. So suppose you have a certain distribution, it concentrates when n goes to infinity because it decays exponentially with n everywhere except some point where the rate function is 0. So in general, what you'll see is that the rate function is positive everywhere except at some point. That point has to be a concentration point because where the rate function is positive, you have exponential decay of the distribution. And so that point here is the point where you don't have it, so the distribution has to concentrate there. So a 0 in the rate function will correspond to concentration, and it will correspond to exponential concentration. And this is the emergent determinism. But the shape of the rate function itself will tell you how fast or the distribution will go down to 0, and it will tell you also whether the distribution is skewed, and then so on. I'll show you some examples later on where the rate function is not necessarily like a simple parabola like here, but this is the idea. So knowing the rate function is nearly the same as knowing the shape of the distribution because you've extracted the dominant part of the distribution and then you've encapsulated that dominant part in the rate function. So this is why finding the rate function for us is so important. It's just easier than calculating the distribution exactly. We know we don't want to, or we don't have to calculate the distribution exactly because it's got this exponential dominant term. And so we just extract the rate function, which is an easier thing to do. So how do we get...
Can I ask a question?
Yes, please.
So the rate function, really, can I think about this as entropy?
Yes, yeah. You will get, if you apply this to a physical system, the rate function is essentially an entropy, minus an entropy, because in physics we'd put a plus sign there, but yeah. So how do we calculate rate functions? So there are many methods to get rate functions, prove that you have a large deviation principle, and what I'll show is just one such result. It's called the Gartner-Ellis theorem, and this result basically takes the point of view of you're not looking at the distribution itself, but you're looking at the Laplace transform. So you study the generating function instead, which is very natural in probability theory. We do this a lot. Actually, sometimes you take the Fourier transform, so you study the characteristic function, and then you just backtrack to get distribution, information about distribution. So this is a bit of the idea. So you still have that random variable an. So what you do, you calculate the generating function of that random variable with that k there. So this is the generating function. It's just scale with the n there. You take the log that defines the cumulant, and then you take the limit 1 over n. And so we call this the scale cumulant generating function. So this is a function that you're trying to calculate without knowing, of course, the distribution. So there are ways to do this. And so you can calculate that function in many, many cases. And the theorem says that if you can calculate, if the result is finite and differentiable, then you have the LDP for the random variable of interest. So the distribution does decay exponentially with n, and the rate function is the Legendre transform of the lambda k. So the rate function is Legendre. So here I'm writing the Legendre transform in a funny form. Maybe you don't recognize this as a Legendre transform. It's called the Legendre-Fenkel transform. It's just a slightly more general version of the Legendre transform. But if you actually try to locate the maximum, what you take is that you take the derivative with respect to k, and then you get essentially the form of the Legendre transform. So that's interesting. It shows that in cases where you can apply this theorem, then the rate function will be convex because the Legendre transform of a convex function. So here lambda k is always convex. The Legendre transform gives you a convex function. But yes. So this is quite a general result. It was put forward in '77 by Gartner, and then the conditions were generalized by Ellis in 1984. So the version I'm putting here is basically the version of Gartner. The version of Ellis is a bit more technical, but that's essentially the result there. Differentiability is very important actually here, and it relates to the convexity of the rate function. Right, so let's...
Another question, sorry.
Yes,
sorry to interrupt. So does this theorem assume that these random variables are independent?
No, so here actually I'm not even talking about the nature. I'm not even defining what an is. An could be anything. So even here I'm just saying I have a certain random variable. It could be a product of random variables. It could be a sum of random variables. It could be pretty much anything. N doesn't even have to be the number of random variable in a sum. It's really, you really have a collection of random variable, and then you have that distribution, and n just goes to infinity, or there's a limit involved here for the family. But here it could be a sum of correlated random variable. But the trick, of course, is now you have this massive object, this function that you need to calculate. And so this is the difficulty. And then we'll see in physics, this is the same difficulty as calculating partition functions or free energies. It's the same because it's a very similar quantity. Now, in the case where you're dealing with a sample mean of independent random variables, what's interesting is that you get Kramer's results. So if you start with Gardner-Ellis and then you take the case that Kramer was looking at, the problem that Kramer was looking at, so a sample mean of independent and identically distributed random variable, then that scale generating function is really just a cumulant because you have a sum of independent random variables. So the expectation factorizes with the log. It just, you have a sum of cumulant and then they're all the same. So the limit disappears. So the lambda k really is just the cumulant as defined by Kramer. And so here now you just play the same game. You can, if you take, for instance, a sum of Gaussian, you can calculate the cumulant. So the cumulant of a Gaussian distribution is just a parabola. This is differentiable, so you can take the Legendre transform and then you get this rate function, which is a parabola. And that's expected because the sum of Gaussian is Gaussian, and so you need a parabolic rate function. So here, this is the rate function. It has a zero. The zero is at the mean because a sample mean will converge to the mean of the random variables. So this is where the concentration point. Here I'm showing the distribution. You clearly see the concentration effect as the number of random variable goes to infinity. And that concentration is all captured by the rate function. Now, because the rate function is a parabola, I know then that the distribution is Gaussian everywhere. More interesting is if you take a sum of exponential, then I can still play the same game. I can calculate the cumulant. This is the cumulant. It's differentiable where it's defined. So I can take the Legendre transform and I get this rate function. And this is, I plot the rate function here. It has a zero again at the mean because the sample mean converges in probability to the mean. That's the law of large number. That's the concentration effect. But now you see the rate function is not symmetric. It's not a parabola. So I can say, well, the distribution will be skewed on one side. In fact, the rate function is asymptotically linear, so the right tail of the distribution is exponential, and then this side then diverges to infinity close to zero. So here I have a tail that really decays very rapidly to zero. So I get a very good understanding of what the distribution is from the rate function. And so this is the usefulness of the rate function. Now you can do this for any of your favorite distribution. You can have a sum of Bernoulli random variable, a sum of whatever, and then you can just crank up the machine there. It's just easier here because it relates to the cumulant function. What's interesting is that this example actually also shows that you don't have a large deviation principle for any type of sample mean. For instance, if you sum Cauchy random variables, you get a Cauchy distribution. So in this case, there's no large deviation. The cumulant actually diverges, so you cannot apply the Gardner-Ellis theorem in this case, and simply because the distribution is not exponential. It doesn't decay exponentially, it decays like a Cauchy distribution. So large deviation theory is not a universal theory. You have some conditions in order to apply this and get the distribution that have an exponential form. Okay, so this is that slide really shows that Kramer is a particular case of Gardner-Ellis, and Gardner-Ellis is really general in the sense that you can apply this to potentially anything that you might be interested to study. You just need to calculate that lambda k, but that's the difficult part. So what people have done is to study in particular Markov processes, and so large deviation theory, I mean, it wouldn't be a theory if it was only something about independent random variables, sample mean of independent random variables. So the main of the work from the 70s and 80s came from applying large deviation or developing large deviation theory for Markov processes. And there are two streams of application. One is you take a differential equation and then you add a small Gaussian white noise. So you have a small parameter here, and then you look at the distribution now of this stochastic differential equations in the limit where epsilon goes to zero. So the large deviation limit in this case is epsilon going to zero. So this is some work that was done by Freiden and Wenzel in the 70s, but if you're a physicist, you actually recognize a lot of the results as coming from Onsager, who looked at path integral of stochastic differential equations in the 50s. So there's another interesting actually historical accident here. So what you see now is that you can calculate the propagator, for instance, the probability, the conditional probability of reaching a certain point x in time at time t, starting from some initial condition at time zero. And what you'll see is that that probability or the density actually scales exponentially with the inverse of the noise, because you have concentration in the noise, and that concentration is very natural. As the noise goes to zero, the stochastic differential equation concentrates onto the solutions of the differential equation. And so this is what I'm illustrating here. For finite noise power, you might have many trajectories going from one point to another, but as you decrease the noise to zero, most of the trajectories will follow a kind of path which is related to the differential equation. And we call this path the transition path or the instanton, and then you can get that path by minimizing some action. So here, this is a rate function in the limit where epsilon goes to zero, and the rate function we know we can calculate from a variational principle. You just minimize some kind of action, and this is the connection with Onsager. This is something that was known. This is the Onsager action for the stochastic differential equation. This is the basis of many things in physics. With this, you can look at transition paths between one state to another. It's the basis also of thermal activation. If you have a free energy landscape and then you're in some metastable state, then the time it takes to reach the stable state we know is exponential with the energy barrier, and that's because the probability of making the transition is exponentially small with the temperature. And this is the result from another Kramer K from physics, which is related to chemical reaction. And people have applied this idea to many other systems since. You can study actually transition paths also for non-equilibrium system, which goes beyond the original Kramer escape problem that was studied for equilibrium systems. So this is one stream of applying large deviation theory to Markov processes. Here you have a low noise limit. What's closer to the idea of taking sums of random variables is to do large deviations for Markov processes in the long time limit. So here you can take, for instance, a Markov chain in discrete time, and then you can look at a sample mean for the states of the Markov chain. Or you could look at a process which is continuous in time, and then you look at the fluctuations of the sample mean, but sample mean now being an integral in time of the process. So here I take the specific case where you have a given process, x of t. This is the random variable that you're interested in. We call this an observable in physics. So you have this AT, which is a sample mean, so the integral in time of some function of the process. And then what we know is that the distribution of that observable will go exponentially, will decay exponentially, but now with the integration time. So that's the analog of the number of random variable in the sum. And in this particular case, in this regime where you look at the long time limit, so here t goes to infinity now, the rate function is obtained from the Gartner-Ellis theorem by doing a spectral calculation. So we know here that lambda k, the scale commune generating function, will be the dominant eigenvalue of some linear operator that we call the tilted operator. So I don't want to spell out the details, they're quite technical, but the upshot here is that calculating large deviations for this regime is equivalent to a spectral problem. So it's a difficult problem. If you apply this to physics, then when people have done this, you can study physical systems that model non-equilibrium systems like molecular motors, and then these quantities relate to thermodynamic quantities like the work done by or the energy expended by molecular motors. And it's related also to many other applications like free energy estimation. Also in engineering, it's related to filtering and detection, even to stats actually. So you have the same picture. You have that rate function. It has a zero in many cases. That's related to concentration, and yes, so that's the same picture. So this is just to give you an idea of how it's being applied, and now I'll go to the physical applications. But the important ideas here is that you're dealing with a random variable whose distribution decays exponentially with some parameter, and that parameter will depend on the application that you consider. It could be a low noise limit, it could be a long time limit, it could be many random variable in a sum, but it could be also a product. It could be a product of many random variables, and so the nature of n will be determined by the application. The fact that you have this exponential actually then explains many things. It explains an exponential concentration, so it explains a concentration effect for the distribution, which is related to the law of large number or the ergodic theorem in the case of Markov processes. So concentration will determine a number of typical values, typical states, and these corresponds to minima of the rate function. There could be more than one minima. Here I'm showing just the rate function, again, cartoon rate function with one minimum, but you could have many minima if you have higher dimensional space. And so you can have many competing, actually, concentration states. The central limit is included here in the sense that if you do a Gaussian expansion or a parabolic expansion of the rate function close to a zero, then it determines Gaussian small fluctuations. But the rate function, like we've seen for the exponential case, can be something that's highly non-parabolic, so it will describe in general non-Gaussian fluctuations. And out of the concentration, then again, I want to stress this concentration effect, that's the emergent determinism. If you look at all the sequences of random variable, all the configurations underlying AN, if you look at the many particle system or sum of random variables, then you'll see that most configurations are typical. And there's only a small set of all the possible configurations that are atypical, and that set is just shrinking exponentially. And that's because of the concentration. Okay, so if you look at a sample mean, but you look at the sequence of random variables that give you a certain value of the sample mean, then you see that most of them actually will have a sample mean close to the mean, and that's the concentration effect. Okay, so these are the basic ideas. What I'll do now is to apply this to equilibrium statistical mechanics and then non-equilibrium to give you an idea of how we apply this in physics, and starting with equilibrium systems. So here we follow very much what Boltzmann did in the first place. Actually, Boltzmann was, of course, also involved in establishing statistical mechanics. So the idea here is that you're looking at n particles. So you have a system with many particles, and then you have these particles here, and then you can label the state of each particle, and that will define the microstate. That's the microscopic configurations. That's the microscopic picture. We, as observers, we're not interested in describing that microscopic level. What we do is that we measure something which is a global function of the configuration that we call the macrostate. Now, in English, it's a bit difficult to distinguish microstate and macrostate, but I'll try to, you should follow me here. So this is the observer measuring that macrostate. And what we're interested in is to find a distribution of the macrostate. So the probability that the macrostate takes on a value m, this is the sum of all the probabilities of all the configurations leading to that value. So this is just a normal probability formula. So we want to find that distribution, but again, in many cases, it's just impossible. So what we're expecting is that this distribution has a large deviation form. So we'll try to extract the rate function, which in many cases is an easier problem. Out of the rate function, we will be able to locate the typical values of the macrostate, and these will correspond to the equilibrium states. These are the states that we see macroscopically with overwhelming probability. But there are fluctuations around the equilibrium states. They're exponentially suppressed, but they're still there. And so we can study with the rate function those fluctuations. And here, the large deviation limit is the thermodynamic limit. You look at very large systems, so the large parameter here is n. Now, how do you actually specify the stochastic model? How do you specify the distribution for the different configuration? This is done in physics by specifying what we call the ensemble. Whether the system has fixed energy or fixed temperature will just determine different probabilistic models for the system that you look at. For instance, if you fix the energy of the system, then you should use what we call the microcanonical ensemble, which says that then the probability for each of the configurations will be the same if they have the same energy corresponding to the fixed energy of the system. So all probabilities in that case will be parameterized by the energy. If you change the energy, you change the distribution. But what remains is that the probability for the macrostate will go exponentially down with the number of particles. So you do have an LDPs. And if you follow Einstein, actually this can be derived from Einstein, and it's consistent with Einstein because Einstein postulated that probabilities are exponential with the entropy, but we know that the entropy is extensive. So up to a sign, Einstein postulate is the same as postulating that you have a large deviation form for the probabilities. What's new now with large deviation theory is that you don't have to postulate this. You can actually derive that result from first principle by specifying what the probabilistic model is, and you can derive the rate function directly mathematically from a cumulative function or by other means. So you're really putting Einstein's postulate on mathematically.
Can I ask you a question?
Yes.
So in this derivation you just talked about, isn't there a lot of assumptions about what the microscopic system is?
Yes, there'll be lots of so I'm really glossing over the whole a very difficult calculation here, right? This calculation you can do easily, say, for the perfect gas or all models that were treated before. But if you take something with interaction, then calculating that rate function is very difficult. And in fact, it's the same as calculating the free energy of the system, calculating the partition function. And so you need some condition to have the existence of the partition function, or to have the existence of the scale current gyrating function. So in a way, actually, here there's not much more than what was known already from statistical mechanics. It's really just a rewriting in large deviation language of what was known in statistical mechanics, especially if you look at the canonical ensemble, where now the configurations are weighted by the Gibbs distribution. So here the parameter is the temperature or the inverse temperature. So here actually getting the rate function is exactly the same as calculating the free energy of the system for that macro state that you're considering. So if you look, for instance, at an Ising model with interactions and the macro state is the magnetization, then calculating the distribution for the magnetization is the same as calculating the free energy for the Ising model. And then there will be conditions, of course, to make sure that the thermodynamic limit exists. So here, the existence of the large deviation function is exactly the same as the existence of the thermodynamic limit. The partition, the free energy exists in the thermodynamic limit, the entropy exists in the thermodynamic limit. So there should be conditions on the interactions to make sure that these functions exist. Yeah, so this is, yes?
To move then again from this, between these two ensembles, you can do so by Legendre transformation?
Yes, so they're connected by duality. The entropy as a function of the energy is related to the free energy as a function of temperature, and that's related to how actually you're weighting distributions in a canonical ensemble with the Gibbs distribution. It's a slide I used to have, but I don't have it now, but I used to actually explain this. I'll give you a reference where this is explained. So again, this is just a rewriting of what we know in statistical mechanics, but in the language of large deviations, to emphasize that now probabilities are exponential and it's related to the free energy or it's related to the entropy, depending on the ensemble that you look at. What you get out of this is the exponential concentration again, and the fact that equilibrium states corresponds to the minimum of the rate function. So if they, on the macrocanonical side, then if you minimize the rate function, you will maximize the entropy. And this is known. The equilibrium states for the macrocanonical ensemble is the state that maximizes the entropy. For the canonical, it's the state that minimizes the free energy. And then this was known actually from Landau in 1937. Like a basic example where you can do the calculation is for the perfect gas. So here I'm just illustrating the kind of calculation that you would do. You have a gas. Here I'm looking basically at the Boltzmann problem. You can determine the velocity of each of the particles. So here I'm just putting a color, say red for high velocity, blue for low velocity. So this is a bit of the cartoon picture that you have microscopically. This is the energy. And then you're looking at the velocity distribution. So for a given snapshot of the system, you could potentially actually measure the velocity distribution and then the histogram of velocity that you have in the gas. Then you leave the gas evolve, and then you can at a different time recalculate the distribution. So that distribution is an empirical distribution, it's a random object. What you want to calculate is the probability of this, and so this is the Sanof problem in the continuous limit. And this is Boltzmann's problem. And then what you see is that most configurations of the perfect gas will have an energy distribution or a velocity distribution that follows the Maxwell distribution. So you have a huge space of configurations, but again, if you just sample configurations at random in that gas with collisions, what you'll see is that most configurations will have a velocity distribution close to Maxwell. So this is the concentration effect. Moreover, if you measure the energy of that system, even though it's a thermalized fixed temperature system, the energy will concentrate in some value. That's the equilibrium energy of the system too. And then you have exponentially small fluctuations around that equilibrium energy. So this is really like a simple application for the perfect gas. Now, if you look at a real gas with interactions between particles, then it's a lot more complicated, if not impossible, actually, to get the distribution. You could get this, of course, from simulation and then realize that you have that large deviation principle. Okay, so I just want to give you an idea of what's going on when you apply this to equilibrium. Equilibrium is difficult in terms of calculations when you're dealing with correlated systems or interacting systems, but there's no time there. It's just really a static system. You're just starting from a probabilistic description of a bunch of particles, and it's a fixed distribution that you use for the configurations. When you apply this now to non-equilibrium system, the difference is that time actually appears in the description. So now you modeling a physical system as a stochastic process.
So we have a question.
Can I ask you something just about the equilibrium part?
Yes, please.
Does large deviation theory bias anything? Because if you come from a physics perspective, yeah, we could do that calculation for.
Yep.
Right.
So
we can, find corrections to the Stirling whatever approximation, and then we have 1/n corrections to stuff. So
yep.
What? Yeah. Sorry for being critical. But
no. It's a fair criticism, and I get it all the time. Because of course you're presenting, especially when I present something like this, I'm just translating something that's been known for 100 years in a new language, and so physicists will query about, why should I use this language? There are a few advantages, and one is that now you see that it's more than just physics. It's really, there's lots of mathematics behind this, and what you gain is the conditions that are built in large deviation theory to tell you when you should be expecting a large deviation principle. So this is good. Then you also have new techniques for calculating free energy. So this is something that we've used actually, especially, so when I did my PhD, I worked on long-range interacting systems. So for instance, like gravitation, so particles evolving under the action of gravity or gravitational interactions, or mean field systems. So systems that have very long-range interactions. And then what we've realized for those systems is that rate functions are not convex. And this is something that actually was not realized in physics, because they thought that entropy was always convex. But what we're able to show is that if you really start from a large deviation perspective, then what you get is non-convex or non-concave entropies. And in this case, then you have to calculate these entropies using other methods which were already known from large deviation theory. So we've discovered in a way like new physics from that perspective, but also added new techniques to calculate entropy and free energy. So for instance, people are using now large deviation techniques to calculate free energies for spin glasses. Right. So there's the replica method, which was developed by Parisi for doing that calculation, but there are other methods coming from large deviation theory to obtain free energy of disordered system. So there are some advantages. But the one for me that's kind of, it's positive, and I would really like emphasize that one is the kind of unification that you realize with large deviation theory. You really start only with this idea of large deviation principle, and then you get concentration, you get equilibrium states, you get fluctuations that are Gaussian near equilibrium states, and so it's something very general. And then the real upshot, I think, is that when you start studying non-equilibrium system, you have exactly the same formalism. So you can establish.
Sorry, can I also ask a question? I'm trying to go.
Yes.
I mean, this is very much related to the previous question. So you seem to always have to meet the thermodynamic limits to actually get this result.
Oh, yes.
And of course, we know that things like the Boltzmann distribution even apply to single atoms. So can you say something about that? Why is it that you seem to have this n to infinity limit, whereas in the regular statistical mechanics, we can apply this to a single very finite systems as well?
Yeah, I mean, I think what you referred to is the canonical ensemble. Canonical ensemble has an infinite heat bath, but that system here can have only one particle if you want, and that's going to be still given by a Gibbs distribution for the one particle.
Precisely, yes.
Yes. But the thing is that if you have one particle, you have no concentration of measure. You have no concentration. You have no the stuff that we see at the thermodynamic level is always in the thermodynamic limit. If I look at the table and I see that it's got a fixed temperature, it's because it's a big system. Of course, I can do thermodynamics for single particle, but then I don't have large deviation principle for that single particle. I just do normal probability theory.
So you're saying that the fluctuations are just very large?
Yes. And then they're not exponentially damped in any way. It's
thanks. All right.
Yeah.
Yeah.
We'll come to this actually when I get to non-equilibrium, because now people are doing that kind of experiment where they look at very small system. And so when you do what they call stochastic thermodynamics, you look at the thermodynamics of small systems, then you see that they fluctuate quite a lot. And indeed, you don't have that thermodynamic limit. So this is the picture here. So the picture is very similar, but the difference again is that you're modeling your system with a stochastic process. It could be one or more particle. You could have external forces. You could have external heat or particle reservoirs. The system might be driven. It might be equilibrium or non-equilibrium. So here the description will follow from the stochastic process. So you have an underlying model for the stochastic process. It could be a stochastic differential equation, a jump process. Of course, we'll take Markov process into account because they're simpler to study. This is what I'll do here. But you have that dual picture of microscopic configuration, which is just the actual path of the system. And then us as observers, we measure something else. That's what we call the observable. And then the goal is to find the distribution of the observable. A classic example is particle or energy transport. You have a hot reservoir, a cold reservoir. If you model this as a stochastic process, then you have a process where particles will go from one side or the other. But at the macroscopic level, you have a constant current, but it will have fluctuations. So you imagine that the constant current comes as a result of concentration of measure. So most trajectories actually will lead to that constant current. That's the current you see on average, but you have fluctuations around this. And so this should be, or the expectation is that this should be described by a large deviation principle. So the typical values, so the mean current or the current that you see corresponds to a stationary state. That should correspond to the zero of some rate functions. And with the rate function, you could look at the fluctuations around stationarity. Now here, there are different limits. You can have many particles, long time observation, and in many, many cases, the macroscopic limit where the volume and number of particles go to zero, you can map this into a small noise limit. This is what we call the hydrodynamic limit or the macroscopic limit. So you can study this in effective ways using a low noise limit. I'll give you only one example where we apply this, just to give you an idea. So this is, again, what I've mentioned before, stochastic thermodynamics. So here you have a single particle system. So it's a small microscopic system. It's a glass bead that you put in water. I think you know this. If you just put a microscope on that bead and then you follow its motion, it will follow Brownian motion. If it's small enough, you'll see Brownian motion. What you can do is that you can shine laser onto that glass bead and you can start manipulating. There's an effect that we call laser tweezers. If you focus two counteracting lasers, you can actually trap the particle into the laser field. And if the lasers are small intensity, this is exactly the same as applying a linear force onto that glass bead. So it's a bit like attaching a spring to the bead and then you can move this. So this is done a lot in physics, also in biophysics, because you can attach beads onto DNA strands and then you can pull the bead to pull DNA strands. So these are experiments that have been done many, many times. So the description of this is usually using Langevin dynamics. So you have a Newton's equation in which you have Gaussian white noise because of the influence of the surrounding liquid, so water, for instance. And so you have the friction term, and then you have the force, which is the laser force. And again, in some approximation, it's a linear force. So it's a linear spring force. Now here, you can calculate different quantities like the integrated work that you do if you pull the particle with the lasers, the potential energy gained by the particle under that action, and the heat released by the particle into the environment. And these are all random quantities, they're random variables. They would be related by the first law of conservation of energy, but the distributions of these random variables can be very different from one to another. And so, for instance, I can calculate the probability distribution of the work done, and then we do find that it follows a large deviation principle. Because I'm dealing with a Markov process here, it goes into the long time limit regime I've mentioned before, and so this is related to a spectral calculation, but I can get the rate function out of this. So this is a very simple example where we can do exact calculation because it's a one-dimensional system.
So that is at late times, is that what you're saying?
Yeah, so here I would calculate something that's integrated in time, and I would take the long time limit. And the concentration in that limit is the ergodic theorem. As I pull the particle, then over a long time, the work I'm doing is mostly the mean work that I'm expecting to get. But then I have fluctuations around this that are exponentially damped with time, and fluctuations can come up because as I pull the particle can move in the other direction and can even pull back. But what the result predicts is that this is exponentially unlikely in time. So you have very small fluctuations, not because now the concentration is not coming because you have many particles. You're dealing only with one particle, but the concentration comes from the long time observation. Okay, so that's the kind of template of an idea of how we apply this to non-equilibrium. Again, now the difference is that you're dealing with the Markov process, but you have these probabilities that are exponential, and the goal again is to get that rate function that will give you lots of information about the distribution itself. You can go from that basic example into much more complex examples, and here I'm just putting some pictures and a list of applications that people have studied recently. In particular, particle transport. So if I go back to this model here, people have been studying this for many, many years, using discrete models, using continuous models. So amazingly, this very simple system of transport is very, it's not completely understood in statistical physics. But it was discussed by Gibbs in the first place, like what happens to the equilibrium distribution if you have temperature gradient, if you have transport. And so we're still working on this, and there's lots of large deviation studies around this particle transport problem. People have also looked at bistability into turbulence model, where you have random transitions between two metastable states in turbulence fluid. People have looked also at temperature anomalies in climate models, very simple climate models, trying to understand some temperature anomalies that happened, I think, in 2010 and 2012 in the Northern Europe region. You can apply this also to chemical networks. I've mentioned disordered system. And also random graphs. For instance, for random graphs, you can look at concentration effects with the size of the graph going to infinity, but you can also look at concentrations of random walks on random graphs, or even random walks in the long time limit on various types of graphs. So lots of research now is being done on application, and the other side where there's lots of activities is on simulation. So trying to develop simulation or numerical techniques to get large deviation. As you can imagine, if you're dealing with exponentially small probabilities, you're not going to use Monte Carlo direct simulations because you will never see the kind of fluctuations that you want to study. These are very unlikely. So you need fancier methods like importance sampling to bias distributions towards rare event. And then there are many techniques that have been developed to do this, splitting, cloning, and now there's lots of work on using machine learning to do this. So that's just a list there. I think I'm going to stop here. I think that I'm reaching the end of my time here. So if you want to know more about this, then a lot of what I've discussed here is from a physics report which I've written when I was a postdoc in London in 2009. It's still relevant, but I would rewrite this actually drastically now if I had to rewrite this. There's a lot more known now about non-equilibrium system, and it's certainly something that I would add to that review if I had the chance, but you get the basics there. For instance, if you want to know about that connection between entropy and rate function, then it's explained there. And then it explained also the difficulty of getting rate functions or large deviations for equilibrium system, and comparing this with the difficulty of calculating free energy functions. If you're more on the mathematical side and you want to learn more of the maths, I would recommend the book by Frank Den Hollander. Many of you might know Frank. This is a nice book. I think he wrote this for a summer school or a school in Canada. So it's got some exercise. It's not too mathematical. It really summarizes the ideas very well. And if you're more on the physics side, then I've written lecture notes for a summer school I went to in 2018, and it was published in Physica A. And this one focuses more on Markov processes, so the long time limit and how this relates to a spectral problem. And I'll stop here. Thank you for your attention.
Right, so do we have any questions? I see a question from Velimir.
Yes, thank you. Hello, Hugo. Good to see you. It was great pleasure to follow your talk, as always. Actually, I would have several of questions that I was writing during your presentation. Maybe I could separate the first group of the questions related to extensivity of entropy and lateral extensivity of rate function. So first in the slide, microcanonical and canonical Yes, exactly. You just say entropy is extensive if it grows with n. But what is somehow usual in physics is that this limit also assumes that volume grows with n.
Yes, yeah, yeah.
So
No, I'm
what?
not. Yeah, I'm not putting the volume here. I should put the volume. So what we have normally is that the volume goes to infinity with the density being constant, right? So the number over the volume stays constant. So n goes to infinity and volume goes to infinity. So here, actually, to be more precise, I should put the volume variable. It's just that for simplifying the presentation, I just took the volume out of this.
I think that if we include also volume as linearly grow quantity,
Yes.
if you could go please back to Boltzmann entropy, one of the first slides.
Yes.
Yeah, exactly. So here, so if we go with volume, which is, let us say, extensive or growing with n, then we would need also to consider this that particles are not distinguishable. And we would need to consider Gibbs factor, this n factorial. So
Yes.
how would it affect the whole derivation?
It's the same. So if you look at, I mean, it's not the same. It gives a different result. Of course, this paper by Boltzmann was before quantum mechanics, so there was no knowledge that you could have indistinguishable particles. So here the particles are distinguishable. This is why you can label them. If you have bosons or fermions, then you would have to do the counting differently. But if you follow the counting for the quantum particle systems that we see in statistical physics textbooks, then you would change the entropy, of course, and so you would include the Gibbs factor for not doing the double counting for the energy distribution, and so you get the Fermi distribution or the Bose distribution for those.
Okay, thank you.
So in fact, in the Boltzmann paper, then in the first example, this is the first example he considered. There's no volume, of course, it's just a certain number of particles, but near the end of the paper, then he goes to study the perfect gas, and so he reintroduces the volume, and so now you have the volume, the number of particles, and then the thermodynamic limit is volume going to infinity with a constant density, so the number of particles over the volume stays constant.
Okay. Okay, thank you. And the second question would be related to Sanof result. I think maybe the next one. Yeah, exactly. So here I see that relative entropy is a relevant quantity for characterization of asymptotic behavior of this distribution. And I also see in his paper on the right hand side that it is actually asymptotically explaining the behavior of this distribution. We have a lot of different kind of divergences, and does it make sense to consider another divergence for creating this relative entropy measure in order to obtain maybe better approximation in formula 45? As I see.
Yeah, so you see in the Sanof's paper here, just in the excerpt, first there's a minus sign that he doesn't put, right? So the probability really goes down exponentially. It's not that it diverges exponentially. And then he's able actually to get the correction. So this goes in the way that I was discussing, that the exponential term, the large deviation term, is the dominant term. Everything else in the exponent is smaller than n. And so here he's actually a bit more precise, actually. There's 2n. N capital is the number of random variables that you have. And the small n, I don't quite remember what the small n is. But this is the correction, but that correction is smaller than n, so it really is a correction. Now, of course, you can go a bit like Kramer and try to find the corrections if you want. But this is more difficult. So Kramer is able to do it for a sample mean of real random variables. But if you try to find corrections here for the Sanof problem, it's just including all the corrections beyond Stirling. Right? Because you start from the multinomial distribution. So the multinomial distribution is the exact distribution. And so what you're doing to get the large deviation term is that you take the crudest Stirling approximation to get the exponential term. And then if you want to get corrections, then you just include corrections to Stirling to get the corrections. You could do this. But you can do this here because you have the exact expression of the distribution, of course. If you study physical system, then we don't have the distribution. We have methods to get the rate function, but it's very difficult, if not impossible, then to get the corrections. We don't know what the corrections are, but we're not very interested by these corrections anyway.
Okay. Okay. Thank you. Thank you.
Pleasure.
I see 3 more questions. I don't know what the order was, but maybe Peter wants to start.
All right. Well, yeah, thanks. Okay, thanks, Hugo, for a very well, interesting and clear talk about the subject. As you think, as you can imagine, I'm quite interested in the path type of large deviations.
Yeah. Yes.
Can you go to one of the final slides where you actually show that this is the large deviation expression is exponential in the time. So I think it's a few slides back. Yeah, there, this one. So the large deviation actually shows that the probability to see this work is exponential to the minus time. Now this is extensive in time. Now this is of course so the extensivity in time means, I mean, if you think about it, that the smallest time scales are the most likely to observe, which is counterintuitive, because if you look at a process, then it will take time to occur, and so there must be some sort of an average time that things will happen. And this is very similar to what happens in particle systems, where you have, say, a number of particles, which is probably in an open system determined by, for example, the chemical potential. And so this is the conjugate variable to the. Now, the question that I have is, and I've been struggling for that for a long time. Sorry about that. It has been struggling for a long time. What is the conjugate variable for time here? And so, what is actually the variable that would be equivalent to the chemical potential that determines the time? You know what
I'm not so sure. I think there's different issue of times here. For instance, if you look at more like escape problem, you mentioned those, and then you have a characteristic time for escape, and then you know that the time it takes for escaping is exponential, and then you can get out of this like a kind of rate. This is how we define, for instance, chemical rates.
Right.
So that's more in the low noise limit. You have something that you have a time that actually emerges from probabilities that are exponentially small. Here the time is more. It's more with the ergodic theorem, right? I have concentration of probability only because I'm observing the quantity for longer and longer time.
So you're not agreeing with me that this is the precise equivalent to the extensive variable in other thermodynamic properties, like, for example, in the time independent part, it's multiplying with n.
Oh, it would be, yeah. No, there's analogy. Yes. Like now, the extensive parameter here is time, so it plays an analogy the role of the n going to infinity limit for thermodynamics. And I suppose for thermodynamic, the way we imagine the thermodynamic limit too is that even if the system is interacting, you can divide the system into non-interacting part, and so the number of non-interacting part also scales with n. And so that's why you have the extensivity. Here you have more or less the same, is that if you take a long time for a Markov process, you can divide the Markov process into, because you're integrating something, you can divide the integral into segments that are more or less independent. And so you're basically back to a sum of independent random variables, and then the number of independent segments is proportional to the observation time. So that's why you have that extensivity in the exponent there. Then for the dual variable to time, I mean, here I can get the rate function by a Legendre transform of some cumulative function, and so there is a variable that is dual to time. It's just the parameter of the scale term generating function. So that plays the role of the temperature, if you want, or the inverse temperature.
Okay.
But I think these are just like mathematical analogies. I don't think there's something very deep in terms of physics into this.
Okay, so maybe I would like to discuss this further, but maybe at a later stage.
Okay, and I'll be interested.
I don't know, between Wout and maybe Wout can, Wout says Maritza.
Okay, so well, first of all, thanks a lot for the talk. I learned a lot. So I was wondering in this part that you talk about emergent determinism. I mean, you clearly see that in the limit, the distribution tend to go into the deepest minima. But what happens when you have minima that are exactly at the same height? What does the theory tell you in that case?
It means that you can have like broken symmetries. Like you see this, for instance, at phase transition. I mean, even before discussing this case, I'm showing another case here on the slides where I have a global minima, but also a local minima. So this will correspond to kind of metastable states. They don't decay as fast as those state here, so they might persist for a longer time if you're looking at Markov processes. But if you have a rate function that has truly many global minima, then you might have a situation where the system will actually select at random one of the global minima because of the initial condition or because of the...
I guess that's what I was going, like, if there's the initial condition, does it, I mean, I guess it's hard for me to say now, but does it play some role in this theory in some sense?
It would, yeah. For instance, if you, I mean, you probably know this one, but if you simulate the Ising model using just spin flip dynamics below the critical temperature, actually the rate function for the magnetization has to zero. It's either the plus magnetization, but there's a symmetry. The negative magnetization has the same probability, but which one you reach depends on the condition that you start in the spin flip dynamics. So this is exactly a situation where the initial condition will play a role. So you have broken, like the system cannot actually go from one global minimum to another because you have these exponential barriers. So it's very unlikely that you'll see actually a mixture. You don't see a mixture, you see one stationary state appearing rather than the other, and which one you actually end up with will depend in general on the initial condition.
Great, thanks.
Okay, and Wout?
Hi, yeah. Also, thanks for your very interesting talk. I had some questions about, let's say, the existence of the large deviation principle. Like, what are necessary sufficient conditions for this? Has this been worked out? Is it related to ergodicity or detailed balance in some sense? Or?
Not detailed balance for sure. Like we can do, if you take a Markov process that doesn't have detailed balance, you can still do large deviations for some observables. So that detailed balance is not something that's very fundamental in the theory. It just, in many cases, it simplifies the calculation. So for instance, for Markov processes, I've mentioned that the calculation of rate function relates to a spectral problem. If you're dealing with detailed balance systems, then the spectral calculation is much easier. And this is explained in this set of lecture notes. If you're dealing with an nonequilibrium system, it's just more complicated, but the formalism is the same. So then for conditions for the existence of the large deviation principle, this is quite difficult. The understanding, I'm not sure there's a clear-cut answer or a definitive answer here. What people understand is that you need the existence of generating functions. So you need, if you have the existence of generating function, and in particular this scale Cuban generating function, then you have a large deviation principle. Whether you have a convex or non-convex rate function, but you'll get a large deviation principle. So usually you're not expecting any large deviation principle. If you calculate this, you get infinity or you get zero everywhere. If you get infinity, it means that the tails of the distributions are fatter than exponential, and if you get zero everywhere, it means that the tails are actually thinner than exponential, so everything decays faster than exponential.
But suppose that it is zero, the scaled cumulative generating function, or the rate function is zero, then I mean, is there still something you can say about subleading terms, like 1/n terms or something like that?
Yeah, so if it decays slower than exponential, then if you try to calculate this rate function, you'll get zero everywhere. So this just says that you're not looking at the right scale, right? So add the exponential scale, you get zero because there's something else going on. It's all in the correction. So in this case, there might be method to get the corrections, but this is rather difficult. And then a clear example where this is not going to work again is the sum of Cauchy. If you add the exponential scale, you get a rate function which is zero. Then you try to get corrections in the exponential, you still get 0, 0, 0, because the whole thing is power law, it's not exponential. So in a way, looking on the exponential scale is the wrong scale in that case.
Okay, thanks. Thank you.
And I see Jay also has a question.
Yeah, it was about the non-equilibrium, one of the non-equilibrium cases you showed, in which there was this kind of transport that you said was not really understood. Yeah, exactly in that picture. If there was a temperature gradient, could you explain what is the issue with this?
Yes, well, the first is a modeling issue, because you can model this in many different ways. You can model this realistically using particle models that interact and collide. So you can do molecular dynamic simulations, or you can try to model this really as a molecular system. But then doing large deviations for this is very difficult because the model is so complex and realistic. Then trying to calculate probabilities for this is very difficult. So what people have done instead is that they try to model this with a much simpler model. And the kind of model that people have looked at is particle model on lattices. So for instance, exclusion processes or zero range processes. So here I'm showing this one here. That's my extra slide for the question. So you have entry rates at some rate, and then you have exit rate at some other rates. And so here mimicking different temperatures is having different entry rates and different exit rates. And you can put now a kind of interaction, which is a Tory interaction. It's just the exclusion interaction. If a particle is on the side, you cannot jump another particle there. So that's a bit like a collision, if you want. So this is called the exclusion process. This already is quite difficult, but people have been able to solve that system, to find the stationary state of that system, but also you can look at the integrated current, or you can look at the density for the different sides, and then you can find large deviations for this quantity. But this is really forefront of mathematical calculation. So already for a system seemingly as simple as that, doing large deviation calculation is really something. It's beyond what I can do myself. And so,
but at the macro scale, it's just diffusion, or?
Yeah, so this is what people do. Then instead of looking, so this is one possible avenue. You model this using a particle system on a lattice. So it's what we call a Markov interacting process. Or the other avenue is that you model this using field theory. So you say you have a kind of transport equation, which is Joule transport, but the current itself is noisy. So in the simplest case, you would have a kind of field theory where you have the current is perturbed by a Gaussian white noise in space and in time. So that's the other avenue. So here you have really a macro evolution and then you can relate the temperature difference to the properties of the transport here. So this is a more macroscopic approach. It's a more phenomenological approach, but it gives a lot of the physics also. Here you can also study large deviation principle. For instance, you can study the density at a given point or the integrated current, and it will scale with the inverse of the size of the system. So this is what I mentioned before. There's a small noise parameter here that comes from the macroscopic limit, because what's happening here is that as you take the system bigger and bigger and bigger, you'll see the deterministic limit of that system. That's the macroscopic evolution. That's the transport equation that you see at the macroscopic limit. If you want to retain some fluctuations, you put the noise in the current, so it's still conservative. And then you see that you have exponential concentration around the hydrodynamic evolution of the macroscopic evolution. So there's lots of work on this. There's been lots of work, I would say, in the last 20 years. Yeah, and this is it's using large deviation language and technique. So it's been quite interesting actually to develop large deviation itself. Even mathematicians working in large deviation theory have been interested in those systems.
Thanks.
Okay, I don't see any more
Yeah,
questions.
there's one more.
Oh, sorry, Kelia. Yes, go ahead.
Thanks. So thank you very much for the talk. It was really nice and very clear. I have a question that is related to a comment that you gave on Wout's question earlier about the large deviation for non-exponential problem. And so I know it's possible to, for example, calculate, let's say if you have a random walk that is random variables that is sampled from a power law distribution. You can calculate the probability that the sum of the random variables is larger than a certain value. So the rare events, let's say. And I was wondering if there is a kind of a general maybe it's a street question, but is there a generalization of large deviation for things that are non-exponential? So instead of having exponential something, exponential minus I of a, you would have n times I of a, you would have something like 1 over x, or sorry, so let's say 1 over I of a to a certain power or something like that.
Yeah. I've been trying to look at this myself actually, but there's not much because the short answer is no, there's no generalization, because it seems that when you look at cases like this, then the cases that you study will really dictate what distribution you see. So the only other general class that we know is the sum of anything that's power law, we actually will stay power law also. So that's the Nedenko central limit theorem, more or less. So for instance, the sum of Cauchy is Cauchy, but you can generalize this to other type of power law random variables. But except for that case, which has kind of retained the power law structure, if you don't have the generating function, then when you sum the random variables, you get a result that depends very much on the random variables that you sum. So there's no universal, or there's no general result when you go out of the exponential in a way. So yeah.
Okay.
Yeah, so it's difficult to answer, but it doesn't seem that you get something as general as exponential when you don't have the existence of the generating function.
Okay.
It's case by case more.
I see. Thanks.
But what's good for us in physics is that for equilibrium, it's equivalent to the existence of the thermodynamic limit. So if you have thermodynamic limit, then you have exponential LDP. That's useful for you.
Okay, now I don't see any questions. So let's thank you again.